So, hello everybody. I'm Joel Falcou. I will be your lunch talk today. I will be speaking about a bunch of stuff, and especially our experiences and feedback on SYCL. I will go over that in a week. For people that doesn't know me yet, you probably know me as someone that likes to torture compilers because they are there for that. I've been the author of various C++ library on various teams, and when I should be working, I'm part associate professor at the computer science laboratory in Orsay in France. And I also the co-founder of CodeRecons, which is a company that focuses on training and helping people dealing with C++, with performances, and basically getting their project up to the track they should be on. And during these times, on both sides of this line of work, we had to deal with a very classical problem now, which is a problem of actually getting performance out of complex hardware. So I'm very sorry for the very, very classical slide that is going to come up. But if you don't know yet, which would be probably a big surprise for me, looks like we have a lot of new workload, a lot of new applications where performance are critical. And it's not getting to go any better as time passes. And one of the solutions that were proposed was to have more complex, more parallel hardware to solve those issues, either by using large multi-core systems or by using accelerators. You probably already, or you probably will, play around with trying to program some of your application main kernel onto a GPU, which is probably what most of the accelerator you will be using at some point. Or if you work in a very specific line of work, you may have played around with FPGAs and other reconfigurable systems. And it's all fine and dandy. We can get good performance with those kind of hardware. That's not the problem. The problem we want to address is the problem that working with this kind of hardware is complicated. It's complicated because if you get two of them, different versions of them, you have to basically relearn what to do. You have to know what kind of idioms are needed to get to the performance. And you probably have to master half a dozen of different vendor-specific tools / language / compilers. And yeah, that's a bit of a bummer. And so some people thought about, okay, you know what we should be doing? We should be having some kind of standard to do that. So that's normally the point where I have a slide that looks like this one, Okay, it's KCD 927 for the one that wants the reference. But actually, it's a bit less green than that. What I want to speak about is the SYCL project, which was started a bunch of time ago now by the Kronos group, and which is actually supported by a lot of software and hardware vendors, which try to solve this problem of having one way to manage the difficulty of writing code for accelerators in general and high-performance hardware in a more global context by trying to minimize, let's say, the surprise factor when you come from a more regular language like C++ or C. And the idea was to split apart the fact that there is, let's say, a compiler part, because for some accelerators, you need special compiler paths to generate the code for the hardware and so on, and a more library-like piece of software that everybody can agree on and build on top to do the buildings. And currently, we have there is 5 there, but there is, I think, 2 more now. Implementation of the SYCL standard, ranging from people from Intel to Xilinx, the CodePlay version. If you ever went to a SYCL talk by Michael Wong, you probably know CodePlay already. A bunch of open source testbed and a bunch of academics version of that. So they basically target everything that looks like a CPU or a GPU now. And the point is to try to find a way to do all of that with a modicum of performances and with something that looks like, let's say, a regular developer want to deal with. So what we did was actually to play around with the Intel version of SYCL, which is packaged under something which is called One API, probably heard about. It targets whatever GPU, CPU, accelerator, FPGA you may have, including AMD and NVIDIA ones. It includes a SYCL backend, so you can actually target the SYCL standard with the Intel compiler now, and a bunch of libraries, including the classical, Intel things like the MKL and the DBB things, and tools like VTune and parallel advisors. One change is now that you can actually access everything there as an open source project, which I give there the overarching links, and you can get all of that on any of your device quite easily. We will see that basically you could also get some kind of pre-made Docker image and so on. So you can actually test SYCL quite fast with this kind of systems. But now the question is, okay, so there is this standards, people provide a backend for that. What does it look like? Okay, how do I manage to do anything with this? There are multiple elements in the SYCL programming model, on which I will try to give a bunch of insight. And there is a clear separation between the way you want to orchestrate your code from a bigger perspective and the way you want to parallelize your code in a different set of operations. It's a more fine-grained, explicit style that you may have the habit with tools like CUDA or similar stuff like this. That give you a bunch of components and functions that you can combine to do whatever you want to do in a far more C++-like way than it was before. So yeah, a bunch of links for people that want to try this at home. But let's get started, okay, right? The first key component of a SYCL program is the queue and the device, which is basically abstraction on top of which we will be able to send operation to the actual physical hardware. You can actually map queue to device, and queue will act as some kind of asynchronous pipelines of operation that the device will have to process. You can have multiple queues per device, but you can also only have one device per queue in a classical way. So this is a rough hello world, let's say, where we basically build the queue, and we ask it about which kind of device was actually selected. So if you build a queue with nothing, you just pick some kind of default device, depending on what you have on your machine. It happens to be some kind of GPU there. And of course, you have a bunch of setups where you can actually select different kind of device by using these selector things. There is a more complex API where you could actually build allow and block list based on features you want to have on your device. So for example, you can ask for a device that supports half precision float but not 64-bit floats and has a debuggable action queue from the host and so on. And SYCL will try at runtime to find the best device that fits whatever you are asking him to do. Another important thing is that every information you may want to get about the queue or about the device or any other component from the SYCL elements, they get this generic getInfo introspection function that give you access to information like the device names, the number of cores, the number of computing elements you can get on that, and so on and so forth. And so you can programmatically write complex logic around how to select or prevent use of a given device. So, okay, fine. Well, at some point, you may want to do some computation with this device. And that's where the main change is actually coming from. You may have seen some SYCL example from some ages ago where you get stuff like that, where you have to manually allocate some so-called shared memory, which is a bunch of memory that is accessible from both the main hardware and the device. You have to copy something inside it, and then you work with these pointers, and then you need to clean it up, and so on and so forth. And the actual operation is handled by the queue. The queue thinks as a bunch of functions. This is a parallel for function. You have a single task function. You have other function for computing deploying barriers or stuff like that. And basically, the parallel for just takes a random, regular lambda functions and shove it onto the device. And this lambda function takes a parameter which is some kind of index. We'll go into the detail of that later, which tells you which part of your data you are currently working with. And so I can access the result pointer directly from the kernel and so on and so forth. And then we have to wait for the parallel for to be completed so we can actually have a look at the results because we need to get the data back from the device. And then we need to freeze the result after we are done with that. That sounds quite a lot, look like a lot like, like old school handmade, manually handled memory management. That's not what we want to write actually. So we need to go past that. Okay. Another point which is interesting is the things that we have to wait on the parallel for. A function actually returns some kind of type which is called an event. And you can collect them, you can pass them to other parallel for or other task submission systems, so you can create some kind of task graph. Okay, fine. But I don't want to see those manually allocated things in my code. Okay, that's not what I want to do. I could actually wrote some code using some kind of unique PTR with a custom deleter and whatnot, but it's still too complicated. So something that was pushed a bit further was to try to make the SYCL code look more like idiomatic C++ in the form of having something that looks like we use error2i, that we use the value-based system of dealing with those data and those tasks. So it changed a bit by the introduction of the buffer class. So the buffer class is basically some kind of reference-counted block of memory that sits on both the host and the device that we can construct from a lot of things, including pointers to host data, ranges, pair of iterators, other buffers, and it just handles everything. Whenever you feed it something, it does the allocation on the device, it does the copies, and you know when and how it should be copied back and forth. And when should it be copied back and forth, either because we will force the retrieval of the data, or in a more interesting way, whenever a buffer is destroyed, it fetches the data back from the device just before being destroyed and put it back into the pointer, into the memory pointer you feed it at the beginning. And when we deal with buffer, we need to have a way to access the data inside. And this access to the data inside the buffer is now a bit more explicit. We need to have these accessor types coming in that will bind a buffer to something that we call a handler, which is a special type that just lets you have access to whatever the queue is doing from the host inside your kernel. So we just try to ask for access to the data from the data buffer with my handler, and then I can use it to run a parallel for over whatever the data is accessed, like we did before. And then I can ask for another accessor, which is the host accessor that give me back the result, okay? So I can look at what the data was actually computed on the device. Looks a bit better. We have this buffer thing that has a lifetime to do with biddings, with destructor is doing what we expect it to be, synchronizing the data transfer back to the CPU. Now, the accessors that come in is a bit more complicated. I mean, it adds another layer of complexity, but it's not obvious in these cases, and we'll get to another example. These explicit accessor systems let you actually build more complex task graphs first, and you have a way to specify the actual operation you want to do on your access on your buffer. You can access either as a read-only buffer, like we do for the host one. We can ask for a write-only buffer, or to be read and write, and all those information we let SYCL find the proper way to do all the data transfer back and forth from the CPU and the host. So we are getting there, but it's not yet perfect. It's still a bit clumsy. We just read the data back from the device memory, but maybe we want to put those data back somewhere else, and we want to have a more all end-to-end process going on, okay? So what we can do, for example, what if I want to have multiple operations running on my data, okay? So I'm just converting my secret string, and then I turn it into an uppercase piece of text with the most ugliest algorithm ever. Don't judge me. And there is something interesting there. I submit some task there at the beginning, which is a computation, and then I submit another one. And the most observant of you in the audience may think that, well, where is the information that, I mean, how does these things know? These things know he has to wait for the other one to be done before computing, because I don't want to start computing data in a random way. That's what the accessor is doing. The accessor building and setup through the handler let SYCL know about which operation has to be done before the other one. I'm accessing the same buffer in both of the kernel. I'm accessing data. And so whenever the second submit start is bidding, when you try to access data into PR, it knows that data is currently being processed asynchronously on the device and put it into a wait state. And the fact that you will be able to build those task graphs using this repetition of accessor constructions is a bit more flexible than these event types and the wait and so on. And it's more natural. It looks like a regular code. I mean, you read it from the top to the bottom and you do exactly what you want. Okay, fine. But maybe I want to do something else. What if I want to get my data back into my string up there? Okay, so I put my string in a non-const string now. I can construct it directly from my buffer, directly from the string. You can construct a buffer with anything that looks like a range, okay? And I do my operation. And one way I can do to get the data back is just ask for the data to be readable from the host using this getHostAccess function that will trigger a synchronization and a transfer back from the device. And then I get my result inside my initial containers or string in this case. You have a bunch of operations on your buffer and on your accessors that lets you select different behavior. If you want to have some kind of sync, if you don't care about the result, you just compute it and do something else, but you don't want to get it back, you can change the destination of the transfer back from the device to the host at the last minute by forcing the destination to be another pointer and so on and so forth. And so you can actually craft very complicated task graph and refine the way you handle your communication between your host and your device. Okay, fine, but can we do better? What if I try to use SYCL and all the thing we saw to build some kind that looks like some standard, algorithm? Okay, so this is a very crude, slide-sized implementation, if you see what I mean. The actual complete, efficient version is a bit more complex. You can actually have a look at that. Kronos provides an experimental implementation of a parallel STL using SYCL that is basically hidden behind the SYCL execution policies that do all the bidding for that. But that's how you may want to write it. So let's try to write this for all algorithm that takes a vector and just apply a function in place, but the function will be run onto the device. So you can actually pass a lambda and a vector, you build a queue, you put the data into a buffer, and you submit a task that just accesses the buffer you just wrote, and you do some parallel operation on that. And that's all. Because when I will go out of scope from the for function, I will destroy the in buffer. The in buffer being destroyed will retrieve the data back from the device, put it back into your data vectors, and you get your results. And on your side, you can actually just call the lambda, the algorithm using a vector and a random lambda functions, and it just behaves like you think it should be. And that's the interesting point. That's what we actually liked by using SYCL in this way, is that you can actually use all those components to build, let's say, a C++ 17/20 loops-like component on top of this. And everything is made so it just works intuitively within the scope of the language. The fact that the buffer has this, this lifetime management, that is basically what we want. The fact that we can select the level of granularity we want on the task, on the way we trigger and collate all those kernels, lets you write complex algorithms in a decent amount of time. Okay. Well, okay, fine. You can write code like this. But we can do a slightly better, because if you are accustomed to writing code using CUDA or whatever, at some point you like to specify how many parallel working groups you want to run on your device. We have that, of course, and it's handled by a specific type, which is this ND range things that can be put as the first parameter of the parallel for. And it basically describes the shape in a number of dimensions, 1D, 2D, 3D, the total number of working elements, and the size of the local working groups, which is basically the same as these block thread nomenclatures in CUDA, and then we can run that. And there we can see that I remove the auto. I just put a cycle item 1, which is the actual type which is used there, which represents position into this grid of, of working elements. It's automatically convertible to an integer. It's directly used by the accessors to get to the information. And the item types also have more API, so you can know where is it in the global scheme of things, in the local one, and you can compute, different logic with that. And then what we do is that we start 64 working element by group of 8, and we do the classical, let's check that the one element I'm trying to access is actually inside my size, and if yes, I can just run the function on it. So we have all of that at our disposal, and the question is, okay, fine, I can write these simple things, but is it any good, actually? And to do so, well, let's look at what some other people do with this. We happen to work with some laboratories that is participating into the Atlas experiment at the CERN, and more specifically on the data reconstruction from the particle tracks. So for the people that doesn't know the CERN, it's this huge ring of physics things where you slam protons together at high speed in the hope that they just go boom and spit out a bunch of other particles. We expect those particles to be new, okay? And we have to characterize them. And what the Atlas experiment does, it looks at this collision into a bunch of high energy magnetic fields, so you can know what's going on. Different tracking, the calorimeters, you've got electromagnetic sensors, a bunch of physics. And what we do is whenever a particle is going out, it will eat up a bunch of cells into these detectors at different layers with different level of energy, and it builds stuff like this. We have this kind of pixelized hits on these detectors, okay? And what we need to do is we need to find, pixels that go together and looks like, a track of a particle inside all of that. So this is a slice of a detector, and you have to see this in 3D, so you have a bunch of slices on top of each other, and we need to know where the particle is going. There is multiple elements in these algorithms. The first one is that what we do is what we call the seeding phase, where we take all those connected component pixels and we try to say, oh yeah, they look like they go in the same direction. And then we try to fit an actual track on that using different operations. And we use stuff like Kalman filter and so on to actually reconstruct the actual track by finding the places where the particle should have gone. And then physics happens, and depending on the shape of this track, the actual energy at each point, the physicists know that it's this or that particle, and so on. Okay. So it's actually a bunch of algorithms on top of each other. The first one is a sparse connected component labeling. Then there is this Kalman filter, and there is a bunch of statistical computation done to know if this, those pixels are close together, but are they actually meaningful to be clumped into a single track and so on. And the cool thing with physicists, you give them something that go fast, and well, they try everything that can go fast to do those computations. So we end up having a bunch of benchmarks. So the blue solid line is a multi-threaded vectorized version using some AMD processors. Okay. So the scale is, oh, sorry about that. So the scale on Y is number of events, number of stuff we are detecting every second, number of tracks we reconstruct, depending on the amount of things we are running at the same time in terms of number of data to process. And basically, we see that on most of the hardware we have there, the CUDA and the SYCL version are basically tied, except for some cases. But it's very close. Okay? And I will do this very rough conclusion. That means that if it's okay for particle physicists, should be okay for most scenarios. So we have this different way of dealing with these accelerators. Okay, we have this open standards, which is actually promoted to be something to be usable in a more global way. And the fact that it's open and it's cross platforms and actually easy to deploy and to test is actually a great thing. Our own experiment shows that you can actually be able to write non-trivial actual idiomatic C++ code with it, with a decent amount of performances. And that's one thing I really want to encourage people. Try it, try SYCL if you can, if you're interested into this. It changed quite a bit since probably the last two versions. The latest 2020 specification is full of C++20-like, elements. So we have this range, we have some concepts inside, we have all these very, idiomatic C++ shapes, and we get performance at a decent level. So try it. Tell us what you think about it, and see where this can go. Thanks for your attention, and if you have any questions, I will gladly answer them.